Machine learning fights global warming introduced a machine learning model to identify ionic liquid molecules to make identifying candidates for CO2 storage easier. Among all greenhouse gases, carbon dioxide is the highest contributor to global warming. If we do not take action by 2100, according to the Intergovernmental Panel on Climate Change, the average temperature of our world will increase by about 1.5 degrees Celsius. Finding effective ways to capture and store CO2 has been a challenge for researchers and industries focused on combating global warming, so Amir Bharati Faramani has been working to change that. Machine learning models bear the promise for discovering new chemical compounds or materials to fight against global warming, explains Bharati Faramani, an assistant professor of mechanical engineering. Machine learning models can achieve accurate and efficient virtual screening of CO2 storage candidates and may even generate preferable compounds that never existed before. Bharati Faramani has made a breakthrough using machine learning to identify ionic liquid molecules. Ionic liquids, ILs, are families of molten salt that remain in a liquid state at room temperature, have high chemical stability and high CO2 solubility, making them ideal candidates for CO2 storage. The combination of ions largely determines the properties of ILs. However, such combinatorial possibilities of cations and anions make it extremely challenging to exhaust the design space of ILs for efficient CO2 storage through conventional experiments. Machine learning models bear the promise for discovering new chemical compounds or materials to fight against global warming. Machine learning is often used in drug discovery to create so-called molecular fingerprints alongside graph neural networks, GNNs, that treat molecules as graphs and use a matrix to identify molecular bonds and related properties. For the first time, Bharati Faramani has developed both fingerprint-based ML models and GNNs that are able to predict the CO2 absorption in ionic liquids. Our GNN method achieves superior accuracy in predicting the CO2 solubility in ion liquids, states Bharati Faramani. Unlike previous ML methods that rely on handcrafted features, GNN directly learns the features from molecular graphs. Understanding how machine learning models make decisions is just as important as the molecular properties it identifies. This explanation provides researchers with extra insight into how the structure of the molecule affects the property of ionic liquids from a data-driven perspective. For example, Bharati Faramani's team found that molecular fragments that physically interact with CO2 are less important than those that have a chemical interaction. Additionally, those with less hydrogen connected to nitrogen could be more favorable in formalizing a stable chemical interaction with CO2. These findings will enable researchers to advise on the design of novel and efficient ionic liquids for CO2 storage in the future. A framework to advance green hydrogen production. Researchers invent an all-encompassing optimization framework to design green hydrogen production processes. However, renewables are intermittent, so ensuring a reliable power supply at peak demand times requires an expensive over-installation of capacity. This, in turn, results in excessive energy at times when the demand is not at its peak. This excessive energy can be sold to neighboring countries, states, but a problem remains. If neighboring countries, states don't need the energy, then what do you do with it? With the Uruguayan electricity sector decarbonized, Torres, who focuses on process systems engineering for clean and sustainable energy, saw opportunities for using green hydrogen to decarbonize transportation, along with other aspects of the Uruguayan economy, including the chemical industry. According to Torres, the International Renewable Energy Agency posits that the hydrogen economy is expected to account for 12% of final energy use by 2050 in a below 1.5 degree global warming scenario. But generating large amounts of hydrogen from renewables is not cheap or easy. Green hydrogen results when water goes through a process called electrolysis that is powered by renewable sources. During this process, an electrolyzer splits the water into hydrogen and oxygen. There are different ways to make green hydrogen, but prior to Torres' research, there wasn't a systematic way to determine the best methods for commercial production. This superstructure is a process of all processes, says Torres. We have this superstructure, as we call it, that is a master flow sheet that accounts for all the possibilities for producing green hydrogen from different sources of renewable energy. We can write a model from that, and we can solve that model using optimization techniques. The framework's flexibility allows for technologies to be evaluated in a way that takes advantage of their different efficiencies and costs. To test the framework, she conducted 4 test cases that featured small-sized hydrogen production plants and large-scale hydrogen production. 2 of the studies evaluated the technologies to find optimal combinations and run what-if scenarios to identify synergies, while the other 2 studies aimed to satisfy an application by only considering technology devices already on the market. Through simulations, Torres determined that solid oxide electrolyzers hold future promise, and if we are to choose currently available market alternatives, then alkaline electrolysis is preferred over proton exchange membrane electrolysis. Electrolyzers are key to green hydrogen production, and the insight from Torres' research contributes much needed information on the performance and operating costs of electrolyzer systems. In this model, we used data from Uruguay, but the idea now is to use data from the United States to see if the same processes that I observed in Uruguay will also be optimal in the United States, says Torres. My guess is that they won't, because here in the United States, it's a much larger country with more climate options. For example, you have a desert where there is not much wind but more sun. That would change the economics of the process for sure, but it might also change which type of technology is more relevant for that region. From a process design perspective, green hydrogen production is a much more difficult problem than the problems we have been taught to solve. It's very difficult because of the intermittences. We cannot design a process for a steady state. We must design processes that work at less than 90% or 100% capacity, and we have to be able to shut the systems on and off as required.